Hello and welcome. My name is Henry Nguyen, and I am here with my team to explain to you what we've been researching for the last couple of months. Our team has been looking into research priorities of potential investment for the Australian government, and we have identified that one of these areas is the energy sector. Our power sector is extremely vital and critical to our society, hence the constant investment into energy generation such as solar power and wind power, but this has created the issue of too much energy in South Australia. Therefore, our group has decided to look into clean energy sources and energy storage technologies that would solve this problem while being efficient, cost-effective, and reliable. During this seminar, we will talk about the problem in greater detail, the project requirements, alternative solutions to final design, important considerations, and future work. In this section, we will address why there is too much energy in South Australia and justify our scope for the project. The problem can be linked to Australia's commitment to lower emissions, leading to an unseen problem of too many solar panels being installed. During high sun periods, this causes an influx of renewable energy into the grid. Combined with outdated infrastructure, it has led to the problem of excess energy with nowhere to go. This has led to elimination of excess energy by methods such as exporting energy interstate and curtailing generation during the day.
Throughout the day, the output from solar generation grows. There is less dependence on electricity provided from the grid, and so the demand drops as shown in the graph. South Australia has a minimum threshold of 300 megawatts, so if the state's demand forecast is expected to drop near this level, then the distribution network will have to curtail generation. Although this is a low-cost solution, it's not ideal because one of the benefits of solar power is offsetting your energy bills, and the energy could be used elsewhere. With our designs, we opted to tackle the issue from another angle. In this graph, we can see the future demand in the next few years. By 2023, the minimum demand is expected to be negative, so it was crucial that we try and solve this issue as soon as possible. We took this into consideration as our performance criteria consider the time to complete. If we don't match supply and demand, then the power system will become unstable. This would lead to deviation from the standard frequency of 50 Hz in Australia. Consequently, there will be damage to generators and consumers, and possibly wide area blackouts due to loss of synchronism. In this section, we will explore the project requirements, which include the performance criteria, project management, and risk assessment. It was important to consider the costs as this defines the feasibility of the proposed solutions and whether it is practical to implement. Solutions with lower costs would be beneficial as this would align with the interests of stakeholders and clients. Our affordability criteria was broken down into 3 sub-criteria. These were initial costs, operating costs, and revenue.
We measured the effectiveness of the designs by the estimated demand it could add to ensure that the minimum threshold is not reached. This demand could be added either through exploitation of energy, charging through batteries, or using energy by increasing the load. With more effective designs, there is less of a need to curtail generation and hence less energy is being wasted. Design longevity will be a measure of reliability which ensures the low demand issue can be continuously treated. The lifespan in years will be based on the Renewable Energy Target, which aims to reduce greenhouse gas emissions by 2030. Designs that last less than 5 years will be scored 0 because it cannot sustain the objective for reducing demand in the far future. The maximum score is determined if the solution can remain active for 20 years and beyond. This would also help in aligning with the interests of a net zero emissions target for Australia by 2050, assuming that the design is implemented before this time.
Completion time is another important user need. This refers to how long it will take for the solution to be implemented. We decided to break the completion time into 2 separate sub-user needs, such as time development of the technology and time to construct. So time for development of the technology refers to the one-time time investment cost, whereas time to construct refers to the ongoing time investment costs of implementing the solution multiple times. So this better helps us to estimate the total completion time. So here we have summary of our performance criteria. And our performance criteria uses all the user needs, such as initial cost, operating and preventative maintenance costs, expected value, estimated demand to add, lifespan, time to develop, and time to construct. So we decided to weigh these not equally, and that's based on how important they are to the users. So something such as estimated demand to add, which is the direct problem we're trying to solve, would be weighted higher. So a solution which can deal can add a lot amount of demand will be favored more.
Our project will adhere to a number of assumptions and constraints. Two of the necessary assumptions made were distributed energy resources being identical to reduce the scope and complexity of the design, as well as costs. Another assumption was for each design there would be a pre-existing cybersecurity measure, so we would not need to design them from the beginning. The constraints for our project would be costs, time, quality, and scope, with time being the deadline of the report and scope limited to South Australia. The main stakeholders for this type of project are the network organizations, including SA Power Networks and Electronet. We also have regulatory agencies which define the electricity and legal requirements for this project. Additionally, electricity retailers and retail customers will have stakes in this project.
This is the risk assessment matrix we use to define the risk rating of any safety, security, legal, and environmental considerations of the final design. In our design creation, we propose 3 different solutions. This section will give a brief overview of them as well as how we scored them. The first design would be moving the remaining pool pumps to midday. It was estimated that around 17 megawatts of pool pump loads in SA could be shifted. This would lead to less generation curtailment during high supply. The second design was a virtual power plant. This is a network of distributed energy resources such as solar panels and batteries, which are centrally controlled. This means that at a large scale, energy could be charged and discharged simultaneously. Our third design was an interconnector between South Australia and New South Wales. This particular design would create a mesh that would act as an additional source of exportation and redundancy in case the other transmission line was offline. As we can see by the evaluation matrix table, the second design, the virtual power plant, scored the highest. In this section, we will discuss the final design in greater detail, considering the subsystem interactions and considerations. As shown in the figure, we have the system design decomposition. We identified 3 primary subsystems to explore further. These were the control center, the battery storage, and the energy generation. We prioritized installing battery storage over generation units as we were more concerned with the battery storing excess energy during minimum demand. The infrastructure needed for this design is the physical connection of wires and cables linking each energy resource to the VPP network, as well as a method to monitor electricity and demand in real time. This would require a Wi-Fi communication module for access to the internet and cloud. Additionally, each generation resource would need to be fitted with inverters and a smart meter to monitor electricity usage.
So the next subsystem in our overall problem is monitoring and communication. Monitoring the VPP will include a control center, which would be responsible for authorizing the charging and discharging of the battery network, depending on the forecast, electricity price, and demand. Control center consists of 2 subcomponents, the remote control unit and the energy exchange. Remote control unit allows bidirectional wireless connection to connect decentralized producers and consumers to control the center. Cooperating with smart meters and other grid-related monitoring data, the system can alleviate fluctuations in supply and demand on the energy grid through Tesla Powerwall batteries. During periods of sufficient solar energy, the power generation capacity of solar panels will increase due to sufficient sunlight. The control system will direct part of the electricity into the battery when it detects that the solar panel's power generation is rising rapidly, instead of letting all the electricity into the grid system. As such, the control center consists of computers and data centers requiring access to Wi-Fi and to the cloud.
In terms of getting the VPP online, there needs to be a human resources team, financial, legal, and risk departments. The HR department would be responsible for managing employees with respect to the recruitment process, payroll, training, policies, and complaints. The legal and risk systems would raise safety concerns or issues in the supply chain to the engineering team, clients, and stakeholders. Therefore, there should be communication channels such as periodic meetings established. Financial and general motivations for customers that are participating in the VPP program include reduced energy bills and government subsidies. Revenue from the VPP will be created during its operation time by trading in the electricity market during the day and during the night.
And finally, our last subsystem is safety and security. So, as we mentioned previously, there is a risk of cyber attacks due to the VPP, as it requires a remote connection and online access. Thus, the solution must have defenses against it and measures put in place so that the risk is mitigated. So, for the environmental considerations, the VPP both helps to contribute to net zero carbon emissions and also has some drawbacks. A beneficial environmental impact is the accelerated transition to renewables, as consumers will be earning income and financial benefits when they are connected to a VPP. So this increases the number of renewable solar panels, which helps to reduce the net emissions. At the end of the lifetime of batteries in the VPP, they should be disposed of and recycled in an environmentally considerate manner. Currently, lithium-ion batteries present a consequential waste issue, as there is a lack of recycling, with less than 5% of the 3,300 tons of lithium-ion battery waste being recycled. Battery waste in landfill is harmful due to potential for toxic contamination and fires. Hence, guidelines and policies should be followed to recycle these batteries at the end of their service life. Improper disposal may lead to fines imposed and damage to the environment. The consequence is moderate due to landfill contribution for the and the possibility is extremely unlikely if the guidelines are followed. Hence, the risk for environmental damage from batteries is low.
As there are financial incentives in place for customers enrolled in the VPP network, this would be considered positive social impact. This is due to customers being rewarded with perks, credits, or reduced electricity bills for their contribution in maintaining the grid. In addition, customers would be provided with a backup source of power from the batteries in event of a blackout. This could also indirectly lead to more satisfaction in investing in renewables, as customers would be less concerned about their PVs being curtailed. Consequently, there is potential to be less reliant on non-renewable generation, which would accelerate the transition to using more clean energy. Ethical considerations that must be made due to the nature of VPPs is the respectful use by third parties for solar panels and battery storages. This will include advising customers of the intricacies unique to their situation and fully explaining the intended usage of the DER. This VPP design is greatly beneficial for its effectiveness to respond to minimum demand levels. Overall, the VPP networks have great potential and would serve an instrumental role in the future of the power sector to maintain grid stability, not just in SA but globally as well. Outside of demand response, the VPP would serve a financially beneficial purpose, as revenue can be generated through buying and selling electricity on the grid. For future work, the VPP could be expanded to handle electric vehicles. EVs would provide additional sources for charging during low demand periods. Another avenue of future research includes methods to make the system autonomous, which would eliminate the necessity of humans. Thank you for listening, and we hope you found this seminar interesting, and also to appreciate the grid around you.